So I want to continue and talk about some issues of identification of behavior genetic models, like what is the underlying model that generates the moment conditions that you then use, that you then take the data and try to infer various variance components, and then I want to illustrate it with some results from adoptees and with some results from multiple sibling types. Okay, now to motivate some of our estimators, it's useful to start with a kind of ideal experiment. Of course, in practice, we're using the word ideal for a reason. In practice, something like this is never going to happen, but it sort of helps us focus on the conditions, on what we're ultimately interested in estimating, and then in practice, we are, in any empirical settings, we go out looking for some kind of realistic proxy for the ideal experiment and try to adjust for departures from the ideal experiment as best we can. So here's an ideal experiment that I think will be very intuitive to a lot of people. Imagine a bunch of monozygotic twins, pairs. Suppose that somehow you have a method for holding also their pre-birth environments identical before birth. Suppose that at birth we randomly assign them to different families. What would you do in order to estimate heritability in that case? Well, you could, if you have a very large sample of monozygotic twins that were assigned to environments using the random mechanism, what you could do is you go out, you can measure their height or their income at age 50, and any resemblance under the assumptions of the thought experiment must be ultimately attributable to their genes, right? Because by assumption, we held constant their pre-birth environment, or suppose that the pre-birth environments were orthogonal to each other, and by assumptions, we randomly assigned them into families. And so it turns out that in this setting, it would be enough to just estimate that an estimator of broad sense heritability is going to be the phenotypic correlation between these two twins, between a large number of pairs of twins. Now, why do I like this experiment? Why do I like this ideal this thought experiment? Well, I like it because it also I think it's also useful for thinking through some of these issues of environmental mediation that keep cropping up. So suppose we ran this experiment with a very large number of twin pairs, and we observe their incomes at age 40, and we observe that the correlation is 0.4, say. Okay, so now we know that the broad sense heritability is something close to 0.4. What does that mean? How would we interpret it? Well, it means that something that can be ultimately traced to their genes caused this resemblance in income. And what is that something? Well, without additional data, we can't really say, but it could be. But in the case of income, clearly there are a bunch of factors that determine your income, things like personality, things like intelligence, and it seems likely, at least, that some of these mechanisms operate through personality characteristics. But it's also likely that that important channels are going to be things like, what kind of jobs did I select into? What kind of how healthy have I been? How stable has my marriage been? Like, what adverse environmental events have I been exposed to, etc. Some of which, some of these environmental events, of course, might be caused in part by genetic factors. So it helps. I think, clarify the rich set of mechanisms through which you could generate resemblance. And so whenever you have whenever you see a claim that something is heritable, I think it's useful to think back to the ideal experiment, and then imagine the various processes that could produce similarity between monozygotic twins of the magnitude you need to match the heritability estimate. Yeah.
Even in the way you stated the ideal experiment, I think there's a huge issue that's important in practice that biases up heritability estimates, and that's that the variance of environmental things in terms of adoptive families
Oh, yes.
much less than in actual families because of the screening they put adoptive families through.
So in my experiment, so you're absolutely right, and we're going to get there when we talk about sacerdote. It's one of the many issues I want to talk about when we discuss when we discussed the limitation of many of these research designs. And each of these research designs has problems. With adoption studies, Miles mentioned the first one, it's like environmental truncation. A good chunk of families are simply not going to be eligible to adopt children. You have to show that you've been in a stable relationship. You have to show that you have conditions, a good family environment in which to raise a child. And so there are all kinds of limits. There are also problems that you often, not always, but and it varies across countries. But in Sweden, a lot of the couples who adopt are wrestling with infertility, so they're also going to be older, and they just vary in all kinds of ways. And so then that essentially boils down to a kind of restriction of range problem that is going to depress your estimate of the variance explained by environmental factors. That's another reason, by the way, to look at regression coefficients as opposed to variance components. But we'll talk more about it when we get there, yeah.
So just like while we're still in thought experiment world, like you're kind of getting at like this like true underlying heritability, which like we never really will fully
Yes.
observe. But I was just kind of curious, it seems like there's this like philosophical debate about like what we would want in heritability. Like some people think 0% is ideal, some people think it's 100%.
Oh, yes.
And I think there's some people who think that there's just like, it's not really important. Like, do you have a take on like what kind of world would you want to live in?
I think that Bolz and Guntis have a nice paper on this in the Journal of Economic Literature when they say that empirically, I'm not going to make any normative statements, but when you look in the data, there is like a heterogeneous collection of mechanisms that lead to some people having more resources than others. Some of them we think are perfectly acceptable. Some of them we think are morally objectionable. There's no obvious. Some of these morally objectionable channels may or may not be heritable. Some of the unobjectionable channels may or may not be heritable. So as an empirical matter, I don't think there's any sort of clear connection between people's intuitions about what sorts of inequality are okay and which ones are not, and heritability estimates. For example, in the data, I suspect that people object much more to sources of inequality that boil down to discrimination, whereas whereas I don't know, a lot of people are probably willing to put up with Steve Jobs being rich because you look at your iPhone and you realize where the consumer surplus he generated came from. I'm not saying that's correct, but I think a lot of people have that intuition, and I just don't. It's not obvious to me that it maps in any clear way to a heritability estimate. Okay, so the ideal experiment is useful in part because it leads to comments such as the one Miles made. We think about what we do in practice to try to approximate the ideal experiment, and the many ways in which we have to make compromises and just deal with the fact that reality is messy. Okay. All right. Now, and of course, James, your hand was up. Are you?
I just wanted to say that not so much now, but with this problem of like adoption studies not being representative, I think this claim is often overstated. For example, in 2007, my colleague you and a bunch of co-authors published a paper. Very unusually, he put himself as the first author, which I think shows how important this is to him. He just made various comparisons between an adoption sample that we're actually still studying in Minnesota and various other statistics such as the census in 2000 and so on.
Mm-hmm.
Basically showing that there is not that big a difference between these adopted families in Minnesota and other families in Minnesota. And they went through the exercise of applying, the Carl Pearson selection equations to try to correct various calculations, correlations they calculated. And they show that this basically has a totally trivial effect. In the Minnesota study of twins reared apart itself, the average level of education by the adopted parents of these twins separated at birth was like 10.5 years. You look at various things like the variance of IQ among all the twins in MISRA. It's almost exactly 15.
So okay,
You could
that's
take
interesting.
this further and say, well, even if the Sacerdos study, various measures of like household income, the mean might actually be higher than the rest of the U.S., but the variance is also greater. And then people, when I say this will often respond, well, you know, even if you have a household where there's not much education or income, still, I mean, both parents work or whatever, or at least one parent works. Clearly, there's something different about that from the population at large. But basically, I think the point still holds that this claim is often vastly overstated.
Well, I don't know what it means for it to be overstated, because very often it's not made quantitatively, right? So it's just, this is a problem, and it's true that it's a problem. That's qualitatively correct. And how big a problem is something that one should work out. That's that's another frustration I had with the poli-sci exchange that I touched upon yesterday. There's just like a laundry list of problems is presented, but no attempt is made to sort of quantify their importance. I'm a little bit surprised by what you said. Yeah.
In the Minnesota paper I was referring to, you can read the exact quote in the discussion, but they said, well, you know, we actually went, after doing all of this empirical stuff, we went to the adoption agencies and asked them a bit, and they said, you know, the criteria we apply for who can become a parent, or we think of ourselves as not being in the position to really determine, okay, you're a fit parent and you're not. And so the criteria we apply are pretty loose.
Yeah, I mean, so as I said, I went back and read like the I can only speak about the Swedish data, which I know well, and there I don't have the numbers in front of me, but looking at the sort of distribution of parental characteristics in our sample, there was a very substantial difference between the biological parents and the adoptive parents, and there was also this issue of non-trivial amount of selective placement. So the correlation between the adoptive parents' characteristics and the biological parents were of the order 0.2. So that's not an insurmountable challenge that sort of totally invalidates the research strategy, but it's something to keep in mind, and maybe even something one can adjust for under some assumptions. But again, you know, the extent to which these things are a problem is something I think one should investigate, and it might vary on a case-by-case basis. Okay, so what's the basic idea in behavior genetics? The basic idea in behavior genetics is that you have phenotypes, which by definition are observable characteristics, and you can calculate how similar they are among different pairings of usually relatives, such as monozygotic or dizygotic twins. So there's nothing magical about twins. We can do it with other types of siblings. Then you can use some genetic theory to calculate the expected resemblance between these different types of pairings of relatives under some assumptions. And then you can try to infer the role of the genetic factors by comparing the observed phenotypic correlations with these theoretical expectations. So it really it really boils down to calculating like sample moments of these phenotypic correlations and finding the set of parameters that sort of match these sample moments well. And this way of approaching it this way of introducing the approach might be a little bit different than what some of you are used to, but I think it's sort of the core theoretical idea. So here's a simple causal model to illustrate. We're ignoring the control variables for simplicity. Suppose that somehow we were able to identify a subsample whose values of z are all the same, and we're interested in estimating the heritability in that subsample. Did I see a hand? No. Well, so the first thing we want to do, just to sort of harmonize our notation with the literature, is standardize all these variables. We just divide through by each variable's standard deviation, by the standard deviation of y, sorry. And so now we're left, we can write this as y plus g plus u. So my phenotype is the sum of my genotype plus a disturbance. Okay. Now, and of course, because of the standardization, the variance is going to be equal to 1. Broad sense heritability here is going to be the variance of g over the variance of y, and this other thing is the variance of y we might call environmentability or something like that. Okay, so we have the moment condition that sum of these two things is 1. That's just the standardization, right? So we need a little bit more in order to infer these two things. At least I don't know how to solve one equation with two unknowns. And so there are many ways to get more information, and potentially you can add more than one moment condition, and then you're going to be over-identified. So how would you do that? Well, you can do it with different types of siblings. So let's illustrate. Suppose you could gather data on twins, like James's predecessor Tom Bouchard did, who've been raised apart, and suppose that you satisfied yourself that these come close enough to satisfying the ideal experiment, so your estimator of heritability is ultimately going to be something like the phenotypic correlation. Well, but very generally, the correlation between the phenotypes is going to be a function of three things. It's going to be the covariance between their G's. So this we know. If the variables are standardized, of course we know that this is 1 or something very, very close to 1. The covariance of the environment and a covariance term. Okay. So now suppose that they were randomly assigned to families. What does that mean? Well, it means that we can get rid of these two terms, and that brings us back, and that gives us the second moment condition. The correlation in the twins reared apart is going to be an estimator of broad sense heritability. And notice how writing it this way kind of helps us clarify some of the assumptions we need to make. It's actually not just including in the standardization stage. If you wanted to extrapolate from this estimate to the population as a whole, for example, you would need to assume that the variances of these G's are reasonably representative of the population as a whole. Okay, so if you have this estimate, then this estimate, along with our standardization, gives us one way to pin down broad sense heritability. Okay, so we go out, we draw a sample of twins, we calculate this correlation coefficient. And that's what Tom Bouchard did. I think by now there have been like 3 or 4 studies of twins reared apart. One of them in Sweden, and the numbers you get are sort of are a lot higher than many people would expect. And of course, we saw James's video yesterday that provides some insight into why, perhaps. Now, one thing we can't identify from these data is H2A. We can't identify narrow heritability from just this one this one sample moment. What is that? Why is that? Well, that's because we have no way of separating a narrow and broad sense heritability with just one type of twins. And that's actually a problem that comes up also in conventional twin studies, and it's kind of swept under the rug or replaced by some assumption. And maybe that's fine, but I think it's good to be explicit about the assumption. Okay, so the twins reared apart example is nice for illustrative purposes, but of course in practice we're limited in that the existing samples are very small. In practice they weren't exactly randomly assigned. And so, while incredibly useful scientifically, we probably want to complement that approach with other methodological approaches. So another methodological approach is to study adoptees, which of course until quite recently were a lot more common. So what does the moment condition look like in that case? Well, again, very generally, it looks like this, right? But now, so suppose that you have adoptees who are randomly assigned to environments, then these terms are going to vanish. Sorry, I think this is a typo. Let me see where we're going with this. So there's a typo here. So if you have adoptees, okay, so if you have two siblings who are unrelated genetically but assigned to the same family, well, then by assumption this covariance term is 0, and this covariance term is 0 if the assignment is random, and so any resemblance you observe between them has to be due to environmental resemblance, right? So that's the basic idea behind the adoption design. We'll look at this again with a specific example of sacerdote in mind. Okay, so again, thought experiment here is so that's one thing you can do. You can also, and maybe this is what we had in mind when we wrote this slide, you can also imagine non-twin siblings who are genetically related but who are assigned to different families at random, so completely analogous to the experiment of the monozygotic twins. in that case, again, these last two terms vanish, and what you end up is that the covariance between these two siblings is going to be exclusively a function of the first term. Okay, so whether which moment condition you end up with, of course, depends on what your thought experiment is. Okay, so let's take the example of siblings who are reared apart. Okay, so we're repeating the thought experiment of the monozygotic twins, but with full siblings instead. What would we get? Well, we would get by the assumption of random assignment and that they're randomly assigned to households, we would get that the last two terms vanish, and any observed resemblance is due to the covariance of their G terms. And this you can then back out from, under a specific genetic model. You can break this down into very different components that allow you to make some progress towards distinguishing between narrow and broad sense heritability. And I think in the problem set we work out these first two terms. So suppose that the only two, suppose that all the gene action is coming from the effects of single loci that just add up. Then I think you work to ask out the algebra for why this term is equal to 1/2. So the covariance between the additive genetic factors of full siblings is going to be equal to 1/2, and the covariance between the dominance variance is going to be 1/4, and everything else vanishes by assumption. But you can also solve for these higher order interactions if you want to. Now the remaining terms basically represent higher order interactions between A's at different loci or D's at different loci, and are sort of intended to illustrate the general point that that as the degree of relatedness between the relatives you're studying decays, a greater and greater portion of the similarity is due to this additive component. These other things decay very quickly. Okay, so we make some assumptions. Maybe our assumption is that we think that there is no epistasis, in which case only these two terms are going to come out of the theory is going to say only these two terms matter. So our moment condition is going to be that the covariance, the correlation between full siblings reared apart, is equal to 1/4 times narrow heritability plus 1/2 times narrow heritability plus 1/4 times dominance. Okay. Okay, so we could go out, we could try to gather a sample like this, and we could estimate it with just the full siblings reared apart, where again we're under-identified because we have these two terms on the right-hand side. We only have one equation. Okay, and so this is a kind of common problem in behavior genetics, and there are different solutions. The best one is just to obtain data on more pairs. That's not always possible, though. And so in practice, what people do is they assume that we live in a simpler world of genetic additivity. And it is important to sort of understand that is an assumption. And the assumption basically boils down to saying that the epistatic and the component and the dominance components are 0. And that may or may not be a good idea. It may be that you have other external information that can sort of guide your decision making as to whether that's a good idea. But if that's the model you assume, and the model is incorrect, then the estimates that are going to come out are also biased. That's the point that we try to convey on the problem set. There's a nice paper by Matt Keller that makes this point, and the reason I'm dwelling on it is that I think there's sometimes a little bit of confusion about the distinction between the identifiability of the parameters and there's practical issues of estimation in the literature. Okay, but if we make this assumption of no dominance and no interaction between loci, we get a very simple moment condition, you only need to look at it to sort of see that in order to back out an estimator of heritability under this experiment of narrow heritability, you would double the phenotypic correlation of twins of siblings reared apart, and that would be an unbiased estimate. In practice, though, if we don't live in a world of additivity, that estimate is not going to give you. It's not going to be biased because it's actually going to tell you what, in expectation, what twice times all of these things are. Now, these numbers are small, and at least the higher order interactions, I think there are good reasons to think are often going to be very small. Those biases are small. But if they're not, you're going to you're going to reach the wrong conclusions. Okay, so you might get an upward biased estimate of narrow heritability if you proceed by just restricting the non-zero terms to 0. Yeah.
So you said that the higher order terms become smaller as
Yes.
people are less and less related.
Yes.
Why is that?
So think about the case of identical twins. They're going to share all interactions between loci, right? So they're going to. So the covariance in their in this term is going to be 1 if it exists. The covariance in this term and any higher order interactions because the genes are the same. And then on the problem set, you're asked to work out these results. You can also do it for other pairings of relatives. I don't know if there's a great intuition for why it sort of happens mathematically, but it's certainly true. And it's the fundamental reason why adding more of these sibling types who are less and less related actually buy you a lot of leverage in terms of identification when you're worried about dominance and epistasis. Okay, so we talked about Sacerdote yesterday. Now I want to return to the study, but with the explicit goal of thinking about how, if at all, it addresses the Jenks and Goldberger critiques and some of these issues about how departures from the ideal experiment. Okay, so the ideal experiment. A first thing to note is the sample. He's studying a sample of Korean-born adoptees. You could tell all kinds of stories about their prenatal environments that might confound things. You might have hypotheses about sort of psychological factors induced by the fact that these are transracial adoptions that make it hard to generalize these findings to other settings. Because ultimately, you want to do something like generalize to presumably what you're interested in is something like an estimate of heritability in the US or something like that. You might worry that the children given up for adoption in Korea are not just a random subset of children born, which of course that would be a very reasonable thing to worry about. And you might worry about the characteristics of the adoptive parents being non-representative of the population as a whole. Okay. One thing that one area where he does really well in terms of approximating the perfect experiment is that he seems to have found a setting where there are no obvious attempts, at least according to the adoption agency, of systematically matching children to parents with certain characteristics deemed to be appropriate. It's hard to say just how closely he comes to approximating random assignment, but at least he has some data on things like birth weight, and birth weight of the children is not associated with the kind of home they end up with. So if there's selective placement, the adoption agency must be using some other child's characteristic to enforce that selectivity. Okay, so you can also you can pick at other things like non-responses. Now let's look at the first thing. So this table we didn't look at yesterday, but now that we've talked a little bit about where the moment conditions come from, we can. I think we're ready to sort of figure out where the heritability estimates are derived from. So how would we go about interpreting? So how would we go about using the numbers in this table? How would we go about using the numbers in these tables to back out something like a heritability estimate? Well, so what Sacerdote does is he says, I'm going to assume that all gene action is additive, and so then you'll remember, and then we're going to additionally make the assumption that this covariance between U and U prime is the same if an adopted child is raised, if it's calculated between an adopted child and a biological child. And so the numbers in this column are just going to be estimates of the covariance of U prime, right? This is going to tell you if I have two children who are unrelated and are raised in the same home, what is their resemblance? Well, the resemblance or the correlation between them? Well, the correlation between them is 0.14. And then from that, we can figure out how much of the resemblance between two siblings is due to shared environmental factors. And to do that, we would just subtract this number from that number. So of the sibling correlation of 0.34, about 0.14 is explained by shared home environment, shared environmental effects, and the rest is due to shared genes. If you wanted to get an estimate of heritability, you would just subtract this number from that number, and then you'd have to multiply by 2, right? You have to multiply by 2 because they only share half of the additive genetic variance under the assumptions. So that's how adoptees can be used to just generate reasonable estimates of the variance of variance components. Now, one interesting thing is that, at least on my reading of the literature, there's a tendency for these numbers to be a little bit higher than. So these are basically estimates of what's called C-squared, so often referred to as C-squared in the behavior genetic decomposition. And I think there's a tendency for the numbers you get from adoption studies to be a little bit higher than the C-square estimates that you get from twin studies. It's not unheard of for twin studies to give you estimates of 0 or even negative, which of course is nonsensical, but it can happen either if you have a bias, if your estimator is biased, if there's something wrong with the twin methodology, or just if you have a small sample and there's sampling variability and you happen to draw get a low draw. Okay, but the main contribution of the Sacerdote paper is not, in my opinion, that he generates these new variance component estimates. They are very much in line with the literature. They are, and that is nice to see. But the main contribution is really, I think, how he engages with the Goldberger and Jenks criticisms. So let's turn back to the figure we looked at yesterday. We saw there was this graded relationship between children's income and their parents' household income. We see that among adoptees. We don't see that graded relationship. That suggests some degree of genetic confounding, and suggests that we may be able to learn something about the causal impact of an environmental variable like parental income from studying adoptees. Also notice that by plotting the data like this, you can sort of infer what the you're moving away from the language of variance components and into a world where effect sizes are reported in terms of regression coefficients, and that kind of addresses, I think, that first of all, that puts the estimates in units that are interpretable and more useful from a sort of policy point of view, and so I think that goes some way towards answering the Goldberger critique, or rather, I think Goldberger would agree that regression coefficients is the way you should report these effect size estimates, and that is the appropriate way to, and they are the appropriate way to present your results if you want to think about the effect of some policy change. And then he just shows a bunch of regression estimates between the relationship of children's outcomes and parental characteristics, with and without potentially genetic confounding. And the point here is very simply that the general, and the point here is not that he can make strong statements about the causal effect of mother's education, say, on child's year of education in the absence of genetic confounding. The point is just that by running these sorts of regressions, you can at least start a little bit to unpack the specific. You can find which features of the household are most strongly correlated with children's outcomes in a setting without genetic confounding, and at least that goes some way towards unpacking this bundle U that is basically an abstract latent index and a little bit hard to interpret. So the U variable is something like the effect of the U variable tells you something like the effect of a 1 standard deviation change in some index of family environment, but that's it's a little bit difficult. It doesn't tell us which features of the family environment are important, and so from that point of view, it's limited. And so moving towards sort of these specific regressions reported in units that are more easily interpretable, I think is somewhat helpful. Go ahead.
Can you just walk us through maybe the first column?
Sure.
How to interpret it?
So here we have the estimation sample is the sample of adoptees. The outcome variable is the adoptees' years of education. And this regression coefficient is the coefficient of the child's years of education on mother's years of education, number of children, etc. He also repeats this in a sample where the regressions are run with the own birth children, where there is genetic confounding. And consistent with the figure I showed you with the 2 lines, those relationships are generally stronger. So what this tells you, for example, is that being assigned to a home where the mother is educated appears to do a lot more for you in terms of your human capital outcomes than, say, being assigned to a high-income household. It doesn't mean that the causal factor is mother's years of education, but at least it helps you zoom in a little bit more on what specific. But it does tell you that either mother's education or something correlated with mother's education appears to be important for child developmental outcomes. Yeah.
So you said that the U is the environmental effect at the family level, but should I think of this as just the environment at the family level? Or
Here's the way to think about you. Take a bunch of genetically unrelated children who had identical pre-birth conditions, assign them, form pairs, and then randomly assign each pair to families from the population. Then when they turn 40, go out and measure their resemblance in income. And if you observe an income correlation of, say, college correlation of 0.14, then you should infer that because, under the assumptions of the thought experiment, this resemblance could not have been produced by genetic resemblance, it must have been produced by something that will ultimately be traced to the shared environments in which they were raised. That's the way to think about it. Does that make sense?
yeah, I guess I'm just trying to figure out if the shared environments where they were raised only takes into account the family environment, kind of the deviation of the family environment from the
Yes.
societal environment.
Sure. Yeah, of course.
Lead
Mhm.
societal environment,
Yeah.
but also the societal environment.
No. So it's only going to tell you something about variation within this society. So in an extremely egalitarian society, UU prime we would expect to be much lower than in an extremely unequal society.
But it wouldn't include aggregate shocks, for instance, that affect all
Yes.
families.
Yes.
It wouldn't.
It would not. It would not. No. Yeah.
Does the regression control for the characteristic of the biological parents that these have?
He doesn't have the biological parents. So the Cesarini study has many strengths, but like any other study, is not perfect. And so he can't do that. We can do that analysis in the Swedish data. We have other problems. One of them is that the biological parents allow us to see whether there was selective placement. The answer is yes. And so then we can run these regressions controlling for biological parent characteristics, pretty much everything that's observed in the registries. And it does bring coefficients down a little bit. And maybe there are additional sources of confounding that we're not controlling for. But at least in our setting, controlling for all the biological characteristics doesn't do it. It depresses the coefficient estimates, but only marginally. Of course, if it's true that the children were randomly assigned, then controlling for biological parents' characteristics would only reduce the standard errors, but we don't expect it on average to do anything to the coefficient estimates.
Do we have any idea? So, I understand that under random assignment, sort of internal validity wouldn't be threatened at all.
Right.
It does seem like I mean, I don't know this for sure, but it seems like a non-random subset of the population is being adopted from Korea.
Of course.
And so I guess just the question is how applicable would this be to all of Korea or even all of Korean children or even all of the world's children?
Yeah. So I don't know the answer for Korea. I can tell you a little bit of what I know about Sweden. So So Sweden so basically, it's become very difficult. It's become increasingly more difficult to do adoption studies in the West unless you're willing to do transracial adoption studies where there are other issues of external validity. Okay, but in Sweden kind of gradually relaxed. So in the 50s and 60s, most adopted children were the result of sort of unwanted pregnancies, and abortion was banned at the time. Sort of progressively, the legislation became more and more liberal in the late 60s and early 70s, and so there were fewer and fewer children being given up for adoption, and transracial adoptions took over. And what you see in the data is that the children are predominantly from very young mothers. So there isn't like a single story, but statistically it's quite common for like teenage pregnancies to result in the children being given up for adoption, and from mothers and fathers who are sort of below SES on average. So the children, if anything, are negatively selected in a statistical sense. Now, children with very serious what's it called? Congenital conditions were not given up for adoption. So there's some sort of truncation of range there. That they were instead handled by other government programs. But other than that, but beyond that, I don't think that there was any restrictions on what children were giving up for adoptions. You can try to, and so again, recognizing what you have doesn't approximate, that is not the ideal experiment. You can sort of ask, okay, what can I do to check how big a deal this is? And you can do things like reweight the sample of adoptees, because it's still going to represent nearly the full range of SES. You still have highly educated mothers who give up children for adoption. And so you could try to sort of reweight the adoptees to make the distribution representative on observables to the population as a whole, see how sensitive your estimates are to that kind of thing. What else can you do?
So
yeah.
your regression results and your weight, propensity score weighting results pretty similar?
Yeah, we did not find that it varied very much at all, actually. Yeah, so we had a bunch of reweighted estimates that yielded very similar findings. You could make some assumptions and try to back out how big the restriction of range problem is if you're interested in estimating C-square. The other thing that's also a little bit hard to get at is if you think that the marginal effects of good family environments are high, especially at lower income levels, and then sort of peter out, then maybe you're getting these fairly flat lines because maybe this is just sampling variability, because I imagine that nearly all of the adoptees will be in this range and that these things have very large standard errors. I might be wrong about that. Certainly be true in the Swedish case. So that's a problem that's hard to get at. I think it's fundamentally hard to deal with. And also, if a family was allowed to serve as adoptive parents despite having very low incomes, then maybe there was something else about them that sort of compensated in the views of the adoption agency. So I don't think, my take on these studies is that they is that they're interesting, but you need to interpret their results alongside the rest of the literature okay.
These like Northern European countries have like these great sort of like administrative data sets that are perfect for this
Yes.
kind of stuff.
Yes.
Do you have a sense of like how, like, is there a push to get more genetic data in them, or are they sort of like cautious about that? Or?
The Swedes have a biobank coming up. Let me say something also about Swedish data, yeah. And maybe, I don't know if the Danes who are with us want to say something about Denmark. I imagine it's very similar. Sweden has a biobank that's being put together, but my guess is that it's not going to be ready for use for at least another couple of years. These things take time. They opted for a sampling strategy that has people coming into in person to see nurses in all major metropolitan areas, and that's just a very slow way of gathering data. So they're not really just, you can imagine an alternative strategy where you have people spit into a tube and send it in, and then agree to have everything matched to the administrative records, which contain a lot of information. But that didn't happen. So the answer is don't hold your breath. It's not going to happen anytime soon. But there's a Danish data set with now, I think, 80,000 genotyped individuals. Swedish twin registry has maybe 40,000. So it's happening, but nothing that's on par with the UK Biobank, which is 500,000 individuals. And then I agree that the Swedish registered data in general are an underexploited resource, and I would urge those of you who are interested in doing this sort of work to try to get involved, because there's opportunities to do things that you can't do in most other countries. It's largely a historical accident that Sweden allows these things. We just haven't had any major scandals, and I think that maybe if we did, the rules would tighten. Now, if you want to do that, I can talk to you about the practical details. Maybe over anyone who wants to is interested in this, I can talk to you about it over break. There are some IRB hurdles that need to be cleared, and you have to be prepared to go to either Sweden or one of the other countries. I think maybe the best way to do it is probably to find a local collaborator with shared interests who can help you sort of navigate the process the first time. And once you've done it once, it's not that complicated. But it is maybe this is unorthodox advice, but I do think it's worth. Ultimately, you're going to spend. Most papers end up taking a year, and so you might as well invest a lot of time into getting really good data, because that's ultimately going to have a huge impact on how informative your final results are. Okay, so that was Sacerdote. So how does he address the Goldberger critique? Well, I think in a couple of ways. He tries to unpack C into distinct components. Mother's years of education or log parents' income are not being randomly assigned here, but I think it's an improvement over just an abstract index. And in reporting regression coefficients, not these variance components, the numbers are sort of in units that are easier for us to interpret. The third thing is that, and I showed this yesterday, so I'm not repeating it here, is that in some of his specifications, he also sort of casts this. He thinks of adoption. He describes it as an experiment, and in the language that explicitly is parallel to sort of the treatment effect language that economists are used to. So he discretely defines three types of families, and then he thinks of the assignment of a child to each of these three types as the experiment, and he can estimate the treatment effect of being assigned to families of different types, right? And again, that tells you something about, by discretizing the family characteristics in different ways and looking at the treatment effect, you can in principle start to unpack, what bundle of family characteristics appear to have the largest impact on child developmental incomes. Okay, and that is a question. I think that's an approach. I think that's an approach that is sort of that satisfies the eyeglass criticism. Okay, please.
I think you hinted a little bit on this.
Yep.
But so if we assume that there is a truncation of the distribution of the environmental factors,
Mm-hmm.
does it always bias our estimates towards a certain direction, or is it indifferent?
Yeah, I think you can sign the bias, and I think it's always going to give you a lower estimate of c-squared than the population c-square. So think, and if I'm wrong, Patrick will tell me. But so think about it's basic at least with like bivariate normality. With normality, that has to be true, right? So if you have if you truncate a normal at the 30th percentile or something and calculate the correlation. The R square again. We can work it out over the break. I'm pretty sure it's true. There is a paper by Stuhlmiller in behavior genetics that does this. I don't know if he has an analytical formula or if it's all by simulation, plugging in values he thinks are reasonable. And so you might want to look at that for the calculations. I don't know off the top of my head if yeah.
But it's always present.
So it's always present in the sense that in adoption studies there always is some restriction of range, to my knowledge at least. No, it might be severe and it might be mild. Apparently in Minnesota, the analysis suggests it's not that, it's unlikely to have a major impact, but there is always some restriction of range. And that's because all adoption agencies just do some screening. And so like if they notice something about the environment, family environment, suggesting that it might not be a good home for the child, and they're not going to send the adoptee there. Other questions? Are there any more? Can anyone think of any departures from the ideal experiment that we haven't discussed yet? In the context of the adoption study, we'll turn to twins next, but I just want to make sure we cover them all. So I think we've talked about everything. Okay, so let's turn to twin studies. So twin studies. So pairs of twins, right, are going to have some degree of genetic relatedness, but ordinarily they're also raised in the same family, and so you can't calculate. You can't infer from just a twin correlation the proportional variance that's due, that's the heritability or the proportional variance explained by these shared environmental effects. So the idea of a twin study, and it sort of goes back to Dalton, even though he didn't appreciate the difference between. He didn't realize that there were monozygotic and dizygotic twins. So some people say he shouldn't get intellectual credit for this. But he was the first to think about twins as a kind of useful tool for behavior genetics. But the idea is to compare the resemblance of monozygotic and dizygotic twins. Okay. Well, so how does that solve the problem? Well, it adds an extra moment condition because MZ twins and DZ twins are obviously more genetically similar. They are, however, and so under the assumption that the shared environmental effects are the same, we can just difference that out. Okay. Now we'll talk a lot about what it means to assume that these shared environmental effects are the same momentarily. I think it's again one of these areas where that seems to constantly, every 5 years or so, there's a new wave of controversy surrounding it. Okay, so to derive the standard twin estimator, known as Hawkins Formula, we're going to make the assumption that genetic factors are additive, which means in practice we'll estimate a mix of additive and non-additive genetic factors. Our estimator is going to be biased unless the assumption holds. So what's our first moment condition going to be? Our first moment condition is again just a standardization plus an assumption, I think already implicit here, that the covariance between G and U is 0. Okay. So covariance between, so remember, we said that covariance, the phenotypic covariance very generally can, for any pairing of relatives, can be written as the covariance of G's, the covariance of U's, and a covariance term. So in MZ twins, in full generality, it would be something like this, but where we've plugged in the fact that the genetic resemblance is 1, and we've imposed the assumption that all the gene action is additive. There's no dominance or epistasis. Okay, so is that clear? That's this term. It comes from the fact that GI and GI prime are the same thing, and because these variables are standardized to have, and these have the same variance, and because we assumed that all the gene action is additive, we can replace GI by AI, and the covariance of the two is just the variance because they're the same. The second term is going to be the correlation of these two terms times U square, and the third term is going to be a covariance term. We do the same for dizygotic twins, and here the key we're making a bunch of assumptions by replacing this term for dizygotic twins by 1/2 times H square A. In particular, we're making the assumption that the correct genetic theory is one in which we have random mating and only additive gene action. Okay? This was the assumption made in the 2005 APSR paper. It's an assumption that people make routinely, but ironically, the paper that predated it, the 1986 paper on social attitudes, actually had a richer set of moment conditions that also included a spousal moment condition. But conceptually, that's just another moment to add to the estimation. Okay. So what are we assuming? we're assuming that all the genetic variance is additive. We're assuming that there's no gene-environment correlation. And importantly here, by gene-environment correlation, we don't mean the environment that mediates genetic effect. We mean the environment that varies independently of our Gs. And we're making what I call the equal environment, well, not what I call, but people call the equal environment assumption. And in terms of our notation, the equal environment assumption says that the covariance of U and UI in monozygotic twins is the same as the covariance in dizygotic twins, and we can just define that as U prime. Okay. So what do these assumptions mean? Are they plausible? So let's talk about one at a time. The first assumption is surely never going to be completely correct, and whether or not it's a reasonable approximation or not, I think it really depends on the phenotype. We'll look momentarily at some data that suggests that it's not a crazy thing to assume for a broad class of traits, whereas there are others where one should be wary of assuming it. The second assumption is surely false in a lot of settings. It says that, and to make matters concrete, suppose that the outcome is again like educational attainment. Then you're going to have some genes conducive for educational attainment, and then you're also going to have environmental factors conducive to educational attainment. And presumably over several generations, you would get some positive correlation between these two things. I mean, it seems hard to imagine how that wouldn't be the case, because parents with higher educational attainment are going to, have better earnings. They're going to be live in better environments on average. They're going to be able to supply their children with better environments, and some of that is going to be picked up in the UI term. And then on top of that, they're going to independently transmit their genes to their children. So it seems plausible that this number is not zero, but it's sort of routinely assumed to be zero. But what you can do, though, is ask yourself whether, in practice, your conclusions are sort of robust to violations of plug in a plausible value of. So if all you have is two twin correlations, right? You're limited in the number of moments that are actually the number of parameters that are identifiable. One option is just to fix this parameter to zero, make that assumption, and that's okay, I guess. But you should be aware of the fact that you're making an assumption. Another approach is just to fix this parameter at some value you consider plausible and re-estimate the model and get a sense of how sensitive your estimates are. Okay, and then there's the equal environment assumption, and that's the one that tends to sort of generate the most controversy. I think that's partly because of I think that's partly because of sort of conceptual confusion. So the way we think about the equal environment assumption. So let me give you an example of something that's not a violation of the equal environment assumption. And it's usually the example of BMI again. You observe in a twin study that MZ twins have more similar BMIs than dizygotic twins. Now suppose a critic goes out and investigates the caloric intake of the monozygotic twins, and he finds, surprise, surprise, that the monozygotic twins not only have greater resemblance in their BMIs, but also have greater resemblance in some measure of their food intake or frequency of exercise or anything you think might have an impact on BMI, sugar consumption. And the critic concludes, aha, I've disproven your study because the equal environment assumption failed. What's potentially wrong with that logic, at least in the framework that we've used to think about twin studies? Does anybody want to? Yeah.
Saying genetic factors could have predicted what they and the BMI.
Right. So it could be quite plausibly that the mechanism through which that generated in part the greater MZ concordance was just had something to do with exercise and food intake. And the way we think about it, that is not a a violation of the equal environment assumption. A violation of the equal environment assumption instead would have to be that the component of U that's independent of the shared components. You can always write this component as two parts, right? Something that's shared plus a random disturbance. It has to be that the shared component is somehow different in monozygotic twins. Perhaps because parents look at their monozygotic twins and they think, because these twins are monozygotic, we have an obligation to treat them more similarly. Or perhaps because monozygotic twins influence each other more than dizygotic twins. Question?
I think that's what I was going to
Yeah.
ask. Was like in the thought experiment world, it would be like if you gave like the same parents the same twins, but then just told them either it was monozygotic or dizygotic and that changed the correlation. That would be the violation.
Yeah, so that's sometimes done. So it's sometimes done. So people sometimes try to. I think that would be a reasonable thing to do. That strategy has been used sometimes, or something approximating that strategy has been used by looking at twins who are misclassified. Okay, so Dalton actually has work on that. It's not perfect though, because misclassification could in turn depend on things like the actual realized genetic similarity of the DZ twins and so on. Yeah.
So I was interested in number 2, and I can imagine that I guess there would be a systematic sort of bias depending on what sort of phenotype you're choosing. Some phenotypes lend themselves more to sort of gene-environment correlation.
Sure.
And some phenotypes less.
Yes.
So the first question, I have 2 questions. One is that, can you sort of perhaps anticipate and correct for that? Does this sort of bias your heritability estimates based on the phenotypes? And the second one, does that also extend to number 3? Based on the phenotype, do you sort of see that familial differences can sort of occur?
Okay, so let me just make sure I understand the question. So the first is, can we say something about bias under violations of this assumption? Okay, and what was the second question?
Well, I'm just wondering, like, how your parents treat your monozygotic and dizygotic twins.
Yeah.
Can it also be influenced by what trait you're sort of measuring?
Oh, sure, yeah. It's always going to be trait specific, right? So all these assumptions are trait specific. You can imagine, and let's see if you can imagine, and for some things it might even be plausible. It's not crazy to think that parents, and I'm sure there's a literature on this, and I might be getting the facts wrong, but I'm making a conceptual point. Suppose you find that parents of monozygotic twins are more likely to give them exactly the same clothes, and maybe they really are doing that because they're monozygotic. Unless that actually has some phenotypic consequences, it doesn't matter. And maybe it has phenotypic consequences on something like, something where your choice of outfit actually matters. I don't know what that would be, but it's very, it's hard to see how the effects on most things that we care about would be other than negligible, right? So there's no question that these things are all phenotype specific. I mean, especially number 1. We'll see that in a minute. And on the question of how does this bias the estimates? Yeah, I mean, you can calculate the bias. You might need to make some assumptions because we have 2 parameters here, so you might need to make some assumptions. But if you, for example, you assume that they're the same and equal to some non-zero constant, it's straightforward to just plug it into the moment conditions and say, what do I get if I apply Falconer's formula, even though this assumption isn't true, and then we can back it out. I would imagine that in any realistic setting I can think of, this is a positive number, and that's probably going to allow you to sign the bias. Yeah.
So if the gene environment correlation is 1, then does that necessarily mean that we're going to yield a heritability estimate of 1?
Gene environment correlation is 1. Oh well, I guess then it's not. Then it's not identified. I don't think. What do you mean? So gene environment correlation is 1. So then, but your genotype. So that would mean that in the population, my genotype is perfectly correlated. Yeah. Okay. So.
That's what I'm saying. I guess if we estimated things this way and the gene environment correlation was 1, we would always yield then the genetic factors would explain all of the genetic variation and all of the non-genetic variation. So then we would yield a heritability.
Yeah. Okay. Fine. Okay. So I see. So in some strange scenario where the 2 are perfectly correlated, would pick up all of it. Yeah. That seems. Yeah. That's right. Yeah.
So I guess I have a question about assumption 3. So if it's the case that certain genetic traits are going to be evoking certain environments
Mhm.
from the parents, is it going to be a violation of equal environments assumption? Because kids are evoking different
Yeah, so I don't think of it as a violation of the equal environment assumption. Some might. I mean, some might slap a different label on that and say, you know, anything that's evoked by environment is I'm going to call it something else. And the problem I have with that is it's fine. I mean, it's useful to make the conceptual distinction. The problem is, what does evoked mean, and where do you draw the line? I've never heard anyone sort of answer that question in an obvious way. And you know, whether I have a particular, you know, I might have some disease that would have killed me 100 years ago, and today is easily treatable because I take some medication. And so, does that mean that my genotype is now evoking a particular medication? And if not, why do I use the label environmental when I'm evoking a parental behavior but not other behaviors? It's a little bit unclear to me. Yeah?
So I've been doing some twin studies in educational outcomes, and I've been thinking about like the third assumption, you know, so there's cultural differences in how you treat twins.
Yeah.
I think in the US there's a higher likelihood of dressing the twins alike, and that's not as pronounced in Denmark.
Right.
And I think actually the school policy is to separate the twins.
Yes, very good.
And that would be that
Oh.
assumption, right? So you didn't do that because they were monozygotic.
Yeah, that's right. And I was just about to say, but notice though that the violation in your example is in the opposite direction. So it's it would be because it's making the DZ environments less similar. So there are pedagogical theories that appear to sort of move like they're fashion waves, and sometimes you're supposed to separate them, sometimes not. And so as a result, this is sometimes done. And the person who knows more about this than anyone is actually Nancy Siegel, who featured in James's videotape yesterday. But so yes, that would be a violation if the separation is actually etiologically relevant, right? If as a result of being separated into different classrooms, because they're monozygotic, their test scores at age 16 are a little bit more dissimilar than they would have been otherwise, then that's going to bias. Notice one more thing though. What if I'm ability tracking the students? And suppose that, and so I use some test at 12 to decide whether they're going to take a difficult math class or a easy math class. Maybe 12 is too early, but okay, let's stick to 12. The monozygotic twins are going to be more similar in their test scores, more likely to end up in the same classroom than the dizygotic twins. Is that a violation? That's not a violation, right, the way we're thinking about it.
I guess unless the variation in their ability is like due to differences in birth rate, right?
I don't see why that would be a problem. Differences in birth weight.
Yeah.
Oh, so if you think that monozygotic twins have more similar prenatal environments for reasons that, yeah, so then yes, that's potentially a violation, sure. That's been explored. There's this huge literature on chorionicity, and I think the bottom line is that there isn't much there, but maybe others have. Yeah.
What's the concordance between, like, just typically between dizygotic twins and siblings? Like, how much does that seem to matter? Just because genetically they're the same, right? But environmentally they're slightly different.
Oh yeah, because they're not raised. There's like age and cohort things going on. Yeah, I'll show you some data in a minute. For the outcomes I've looked at, it's usually pretty similar. I have a slide, so we'll revisit that issue momentarily. Yeah.
Yeah, we actually compared dizygotic twins and a dizygotic twin with the closest sibling.
Yeah.
And looked at the correlations in educational achievement, and
Mhm.
saw that the correlation for dizygotic twins were 0.87.
8.7.
No, it wasn't educational achievement, it was cultural consumption. So
Okay.
yeah, sorry, mixing up stuff. And for a dizygotic twin and a sibling, it would be like 0.80. So
Okay.
like very, very similar.
Yeah, I'll show you data from like the universe of Swedish brothers over 3 decades in a minute. Did you have a question? Anyone else? Yeah.
So why is the equal environment assumption only for the twins? Like, why doesn't it also apply to adoptees?
Oh, no, so if you added adoptees, if you added a third moment condition, you would have to make some assumptions about rho adoptees U prime. You have to make some assumption about it. Now, because it's an extra moment, it will also mean that you would have an extra parameter to estimate. You could actually estimate it. There are papers that do that, including one of ours. But I don't think I'm disagreeing with anything you said. Yeah. Dan.
So I love the way you're suggesting that when we think through a particular phenotype, we might want to make a different assumption, like
Yep.
assume a certain correlation maybe based on other evidence, or in Stina's example of the separating the MZ twins, maybe assume that there's a slightly lower correlation in environments for MZ twins than DZ twins for schooling outcomes. It's my impression that the behavior genetics literature generally doesn't do any of those things, that it
No.
generally just makes these assumptions and then moves on and doesn't even, doesn't think about
Yeah,
sensitivity.
they're not
Is
even
that-
stated. I don't think it's always, they always know what assumptions are being made. And no, I agree with you. It's more of a cookbook approach to estimating these models, and I think it's a shame because assumptions and their plausible. Thank you, Patrick. Should be sort of evaluated on a case-by-case basis, I think. And the debate shouldn't be about whether the assumption holds or not. No assumption holds in a literal sense that I can think of, but whether it holds approximately. So I agree with everything you said, and actually that's one of the reasons why we try to introduce the material this way as opposed to just getting straight to the software. I think it's much more important to understand what the software is doing and what you're having to assume in order to interpret the results in a different way. That's much more challenging than actually getting numbers once you have some data. Yeah.
I'm sorry if you already said this, David, but how are you assessing whether a phenotype is more additive versus not? I mean, how are you looking at that?
So we'll talk about it. I'll get back to it when I show you a slide with some data. But the basic answer is that you can look at the resemblance of monozygotic twins, dizygotic twins, half brothers, cousin, and then as they progressively become less and less similar, the rate at which the resemblance could be accounted for by the correlation in the additive component decays at a rate linearly, and the other one vanishes very quickly, and that gives you sort of additional identification. Any more questions? Okay. So here are the three moments you would get under the assumptions of the twin study. The first is just a standardization. So we're going to make the phenotypic variance 1, which means the variances and covariances and correlations are the same thing. Second is that rho MZT is equal to H2A plus rho UUI times U squared. Now, this is an assumption. Without the assumption, like if we were only willing to assume that the G's are the same, then this would be equal to H2G, right? We replace it by H2A. We can do that because we assume that all all gene action is additive.
And that just plays in when we move from the second equation to the third equation. Like by making it additive, we didn't have to add in like the plus 1/4, like H, like D squared plus like 1/8.
Yes,
You know,
that's right.
What the additive
Yes,
trick
yes.
is doing for us.
Yes, that's what the additive trick is doing for us. And then the third moment condition, again, using the additive trick first, or the additive assumption, and then the fact that these two terms are the same follows from the equal environment assumption we made. So we need to invoke all three assumptions in order to identify get a heritability estimator from just twin study data. And notice the fact that these two things are the same. They're the reason we're going to be able to difference out the environment. We can just subtract one equation from the other, and then we have an equation in just one unknown, and the two population correlations we can estimate by drawing a sample of twins. Yeah.
So we made the assumption that the interaction between A and the environment is 0. We could also just assume that it's the same for both. It's maybe too strong, right?
I
we
see.
just said they're the same, then we can difference that in the same way that we're differencing out the U squared term.
But in that case, there could also be interaction with a term of U that's uncorrelated within pairs, and that would be more similar in MZ twins, I think.
Okay.
Yeah. So I think we need to. So I'm not sure that gets us all the way there. Okay. So, and the point, and actually Patrick's question helps clarify. We have to make some pretty strong assumptions in order to get to what's called Falconer's formula. Let's see if we have, okay. And so how do we get there? Well, anyway, so under these assumptions, the variance component is going to have, there are going to be 3 variance components. And let me explain now how let's take the model we've discussed so far and let's explain how it relates to the parameters of the standard model, which is called the ACE model. On the problem set, I think you solve a slightly more general model called ACDE. Okay, so usually what you do is you reparameterize the equations, and so let's just be explicit about how that reparameterization is done. The first is just you define h squared a as a squared. That's the a in the ACE model. You call this term c squared. That's the c in the ACE model, and you could call the portion of the environment that are drawn independently in the 2 pairs. You call that the unique environment, or E, okay, or unshared sometimes. Okay, so we have that U squared, this variable U, we're going to write as its variance is the sum of a variance due to shared things and unshared things. Okay. So in terms of the usual notation of the literature that you'll see in papers, the moment conditions are, well, the standardization says the variance of the additive genetic effects, the shared environmental effects, and the unique environmental effects is 1. The rho MZ correlation, the MZ correlation is a squared plus c squared. The DZ correlation is 1/2 of a squared plus c squared. Now, just solve this equation and replace to get an estimator of narrow sense heritability. You can convince yourself that in this model, just from these 2 equations, I guess multiply this one by 2 and subtract it from the first one and rearrange to get that heritability has to be equal to twice the difference between the phenotypic correlations. And so from that moment condition, we just substitute the things that we can estimate in the data, namely the 2 rows. You substitute in the sample estimates in lieu of the population parameters, and that gives us this estimator. And this is called Falconer's formula. Once you have an estimate of a squared, it's straightforward to also get an estimate of c squared, and of course e squared is just whatever remains in order for these 3 components to sum to 1. Okay, let me just say a few things about things that can go wrong here. So first is you could, and maybe I think this might be on the problem set as well. First, you could end up with an negative estimate of c squared. Does that make sense? Why can't c squared be negative? Like, why can't the true population parameter be negative? It seems odd, right, that a variance component would be negative. Yeah, go ahead.
I don't know if this is good for, but our variance is usually squares. And you can't really get a squared term.
Yeah. Actually, maybe Patrick knows how to do it, but I've never been able to figure that out. Yeah. So that's, yeah, variances, simple variances are negative. But the reason I raise this is that in practice, you might end up with negative parameter estimates, right? And that might be the case, for example, if you have some gross violation of the equal environment. That might be, for example, if you have a lot of non-additive gene action. That's what happens that's what we discussed in the problem set. If you have a lot of non-additive gene action, that's going to increase the resemblance of MZ twins a lot more than the resemblance of DZ twins, right? You're going to try to attribute all of that to the additive genetic effects, and applying Falconer's formula, you end up with if you just do like an unconstrained estimation, you end up with a negative C parameter. So in some cases, the model violations might be so severe that you end up with parameter estimates that fall outside the range of the sort of permissible values. And in those cases, unless the standard errors on those things are huge, in which case you can just maybe replace the negative estimate by the value on the boundary as your point estimate. In those cases, you can be quite confident that there's something wrong with the ACE model, even though you're just identified. right? And that's because we have these other constraints but we actually have some other equations that implicitly place some more restrictions on these numbers. In practice, that isn't all too common, right? So very often, you might have substantial violations. You might have a lot of non-additivity, but as long as this term isn't too small, then that's just going to serve to depress your C-square estimate and inflate the A-square estimate because your model is misspecified. And getting back to a remark I made earlier, this is I think it's a fairly common thing in the literature to use some like fit diagnostic criteria to say that you know my model fits the data well. And to jump from that conclusion to saying that therefore to confuse failure to reject the model in some statistical sense with the notion that the model must therefore be very accurate. Right? So you could come up with parameter values, and this is what you're asked to do on the problem set, under which the bias you misspecify the model severely. You're going to end up with very misleading numbers. Nevertheless there's no hope of detecting it because you have a large value of C. Okay. Please.
Maybe we should wait till after your
No.
application, but I'm curious, so definitely defer this if you think it's better to talk about it there. But I'm curious your thoughts on the common practice of using model fit measures
Yes.
to decide which model to estimate.
Yes. Yeah, so it's a decidedly odd thing that's done in the literature. So what they'll do is they'll have some data set with mono and dizygotic twins, and then they'll have some statistical criterion that says, does the fit decline appreciably if I drop a parameter? And if it doesn't, then I'm just going to go ahead and drop it and assume that it's equal to 0. So, and very often what this means is that so suppose we live in a world where these numbers are generally like of the order 0.1, these numbers are generally of the order 0.4, and so that in typical study you don't have much hope of detecting this, like at a 5% significance threshold. Often what these fit diagnostics end up doing is tell you, oh, it's fine to drop C, and then you end up estimating a model in which rho mzt is just equal to a squared, rho dzt is 1/2 squared, and then you actually have two moment conditions in one moment, and it returns some number. That number and the associated standard errors are then interpreted as they're going to have very, very small standard errors. But all of that is coming from the fact that you just restricted seek to equal 0. And notice how crazy it is to restrict seek to equal 0. The whole point was to use the natural experiment. I'm trying to find where we said it. The whole point was to use the natural experiment and make an assumption that the family environments are roughly equivalent in the sense of the EEA to difference out that component. And now we've just moved on to just restricting it to equal 0. What does this mean? It means we're estimating a model in which the assumption is now that any observed resemblance between the twins is due to their genetic resemblance, when the original purpose of the study was to try to tease apart sources of resemblance that can be traced to you and sources of resemblance that can be traced to genes. So paradoxically, even though you're actually almost always under-identified if you want to estimate something reasonable, you end up just estimating a single parameter and declaring victory because that some fit diagnostic is good. So
what sort of information criterion are they using?
I don't know what it's called. You know?
It's AIC and BIC.
Yeah, BIC. Yeah, Bayesian information criterion. Yeah.
And but then why not just why even have dizygotic twins?
Yeah, exactly. It doesn't make any sense.
You
Yeah.
get a big
Yeah.
data set of
So you just look out for that in the literature. It's just done routinely, and I think kind of at some level, I'm sure people understand that it's a problem, but it's become the norm, and I don't know what to say. Each field has its blind spots and its elephants in the room, and sometimes I think polite people just decide not to discuss it.
common practice is literally to just have a table where you show the fit of an ACE model, an AE model, a DE model, and then you
Oh,
just
yeah.
like
Good. That's another point I should make, actually. Sometimes what they'll do is they'll derive the moment, well, they'll list the moment conditions for the ACE model. They'll list the moment conditions for an ADE model. Then they'll estimate both. And then they'll say that they'll determine that one had better fit than the other and conclude that therefore C squared must be 0. Okay? So after you've worked through the problem set, my hope is the point of the problem set was to kind of help convey how silly that is and why you shouldn't really be doing that. And so if that's not clear after the problem set, actually I'd like to know that because then we've failed. Yeah.
What's an ADE model?
ADE model is a model in which instead of 1 equal to h squared, let me write it down. So instead of these moment conditions, you have, I just want to make sure I use the same notation. So let's call ADE, yeah, that's plus u squared, is that what we're calling it?
Yeah.
Rho mz is going to be h squared a plus h squared d plus nothing. And rho dz is going to be 1/2 h squared a plus h to d multiplied by a quarter. You derive these parameters in the problem set. That's supposed to be a d. When I was in high school, my physics teacher told me my handwriting would get me into trouble.
there's also terms with u squared. So
Oh, am I? Oh, yeah, yeah. So, but those are restricted to 0 because it's an ADE model, right? So we've just said we've assumed that C squared is 0. Yes, I think this is right. And that's just a different. And how is it that the fit diagnostic can even tell you that one is better than the other? Well, the idea is that in the ACE model, right? If you observed that the dz decay is very large relative to the MZ model, given what you would expect under the ACE model, where all gene action is additive, then it must be that there's some non-additive. Then you accommodate that empirical finding by saying, oh, there must be non-additive gene action. But if I add non-additive gene action, I have one more parameter that I can identify, and so I'm going to solve that by saying C squared must be 0. Okay.
So if I say that C squared equals 0, I'm saying there's no correlation between pure environmental.
No, I'm saying a lot more than that. I'm actually. You could actually paradoxically, you're saying that the shared component of U, the component of U that siblings share, just has 0 impact on the outcome. So there are no family effects. Yeah. So you're saying all of the resemblance between the siblings, between the twins, is now due to genes. Okay. And you can see how the actual. I mean, one thing is the identification. There's like simulation evidence on this. The idea that you can sort of separately identify these two things. The identification is really tenuous in most realistic settings. You can identify them separately, but your ability to distinguish between these two factors, even under the maintained assumption that there is no C, is really limited, just because the covariance between the estimates is really, really high. Okay.
So is the moral of that story, like, if we actually think that there's significant non-additive genetic components, we just like need to have more degrees of pedigree?
I would just say, if that's what happens, and if you don't have any, you can go try to get more data, try to see in the literature what is known, to see if you can do some sort of fix. And if none of those things are possible, I would at minimum just say, okay, instead of fixing C to 0, I'm just going to assume a range of values and give you the estimates for each possible value that I think is reasonable. Maybe the lowest estimate I think is reasonable is 0. Maybe the highest I think is reasonable is 20. And then you can just show these estimates conditional on just fixing C at some value, and then readers can make up their own mind as to what's reasonable. That's I think.
Isn't it another option to estimate an ACE model, but then interpret the heritability estimate as something that's in between the additive, the H squared A and H squared G, and just be explicit that you're not pinning down either of those?
Yeah, I mean, that's doing something similar, but kind of replacing the true row, because then in your example, so let's see if I can, so your example is to say, your idea is to say, let's make the moment conditions this, let's see, let's call it like H2G plus U squared. So we accept that there's some broad heritability. Oh, what did I call it? C squared? U squared is fine. Okay. H2 squared, let's just call it C squared just for simplicity. And then rho dz is going to be equal to some parameter alpha, that's the genetic covariance on this factor that we don't know, plus C squared. And then you say, let's fix this at a half and estimate the model. Or we could alternatively just vary alpha at different levels and estimate the model and give the results. And then we get an estimate of broad sense heritability. Maybe that, maybe what you said is equivalent or very similar. But there's no getting around the fact that if you have yeah, there's no getting around the fact that if you have more unknowns than equations, there's only so much you can do. But the thing I would discourage is just sweeping it under the rug by making some arbitrary assumption. Okay, so where were we? All right, so let's move on. Let me just illustrate. So I'm going to get back to this issue of DZ and full sibling correlations. We're going to get back to this issue of the rate of decay and how that allows us to say something more about distinguishing between, identifying C square and non-additive gene action at the same time. And I'm just going to show you some data that's I think contains some canonical findings from the BG literature. So these data are based on Swedish men born 1950 to 1970. So it's all men because Sweden has these, until recently, had conscription at age 18. And at conscription, people undergo a range of sort of psychological testing, and that allows us to just look at a richer set of outcomes. But overwhelmingly, the numbers, I'm very confident that you would have gotten extremely similar results for women. I've never really seen any convincing evidence of correlations that differ between MZ, between female and male MZ and DZ pairs. Okay, so I'll show you some data on educational attainment, height, BMI. I'll also show you some data on a measure of cognitive skills and non-cognitive skills from conscription. How is this data assembled? We went to, we gathered data from on all Swedish men born between 1950 and 1970. We have to start at 1950 because the electronic conscription records start in 69. We identify all brothers who were in, I think, 5 years of age from them. So we have now a bunch of brother pairs. And then we went back to the censuses and checked whether the brothers were raised in the same households, in which we say that they're reared together in every census between age 0 and 18, or if they were raised in separate households, in which case we say that they were reared apart. The registers also have information about adoptees. So if two siblings are reared in the same family, but one or both are not the biological children of the rearing parents, then we know that. Okay. So what's unique? Well, it's an enormous sample, and we also have 7 types of relatives. I should say, credit for putting this together the first time actually goes to the economist Anders Björklund, who did this in a paper with Marcus Jenti and Gary Solon in a book, actually the Russell Sage book, edited by Bowles Ginties and Osborne Groves, I think. And so you can look at that. They applied it to earnings, and we just added in a few more phenotypes that we're interested in, and we sort of reported these correlations in different papers of ours. So you can look at these data, and you can ask, okay, which phenotypes appear to have for which phenotypes do we observe phenotypic resemblance that is roughly consistent with the ACE models? Are there some phenotypes for which we don't observe patterns of resemblance that are easy to reconcile with the ACE model assumptions? And how robust are like ACE estimates from say twins to estimates based on other types of comparisons of siblings. Yeah.
All phenotypes are measured at age 18.
Except for educational attainment, that's ultimate educational attainment. Yeah, but height at 18, BMI at 18, cognitive test score at 18, and this fourth, last thing is a kind of measure of what my friend Eric Lindquist has called non-cognitive skills. It's basically a military psychologist's assessment of how well you would do dealing with the challenges of wartime stress. And it turns out that it's really, really predictive compared to other personality batteries that people have proposed. In fact, it even for some outcomes, like being completely divorced from the labor market, it actually does better than standard IQ tests, which is remarkable. And there have been claims like that in the past, but usually based on small samples. These claims are real. They're based on like enormous samples that Eric and his collaborator Roine Westman gathered. So it's a cool measure, and it captures something other than whatever it is that IQ type tests capture.
Where do you get the educational attainment?
So that's also in the registers. So Statistics Sweden just has very detailed information on people's educational attainment. So I think I said, I forget the details, but I think it's measured, like I have to observe it at least at age 30 or later, or something like that, okay? And these are all data that you could get in principle. Okay, so here's just what it looks like graphically. In the original papers, we showed these data in tables, and nobody paid any attention. And then we put it in a graph, and everyone thinks it's really cool. So I'm just going to show you this, but then we'll switch to the numbers because there's some advantages of the numbers. And so what do you see here? So here, we start with the monozygotic twins. So they're patterns of resemblance. So their height and BMI generally come out on top. So you observe the greatest correlation for those two traits. For the other variables, the correlations are in the range of 0.6 to a little over 0.8. Okay, and then I'm showing you analogous estimates for the same phenotypes for dizygotic twins, full siblings reared in the same home, full siblings reared apart, half siblings reared together, half siblings reared apart, and adoptees. And there may be like two messages. I want like two take-home messages from these data. I'll show them in the tables. Okay. So the first is that as the degree of genetic relatedness decreases, the phenotypic similarity decreases. Okay, holding constant the fact, restricting the comparison to siblings reared together. So if we restrict the comparison to siblings reared in the same home, it's still the case that those who are more genetically related are more similar on height, on education, on height, education, and BMI. It's also the same for cognitive and non-cognitive skills, but I'm not showing you the numbers here. And the same is true if you just look at siblings reared apart. So if you look at siblings reared apart, siblings who are more genetically related are more similar. Okay. The second thing is that generally you see that siblings reared apart are more similar than siblings reared together are more similar than siblings reared apart. So there appears to be something about there's clearly something about being raised in the same family that makes you more similar. And I think the sort of Sassadot style analyses that we've been looking at provide a nice example of serious research efforts to try to uncover what that is, as opposed to just attributing it to this variable C that is not easy to interpret, and it's hard to know what you would do with it, even if you knew the true C. Okay, so those are two pretty cool results, and they're actually illustrative of what you find in the literature as a whole. Okay, so when you look in the literature as a whole, Eric Telkheimer wrote a famous paper in the year 2000 in which he made a number of points. He started out by formulating these three laws. Yesterday I mentioned in passing that the political science results, BG results, were very much in the spirit of the three laws. I'm going to talk about the three laws in slightly greater detail, and hopefully that will clarify yesterday's remark. First law, and I should say, Telkheimer uses the law a little bit, he not in a literal sense. It's not that he's saying that these are universal truths. He's just saying that they're very, very robust empirical regularities, at least on my reading. First is all human behavioral traits are heritable. Second is that typically the effect of being raised in the same family is more than the effect of genes. The way I would put that is, if you have two siblings, for most phenotypes, the bulk of the resemblance can ultimately be traced to genes. More of their resemblance is accounted for by something that has to do with their shared genes, and less of their resemblance can be traced to things that have to do with their shared environment. And then finally, a substantial portion of the variation in these complex human behavioral traits isn't accounted for by either genes or family. That is to say, that in the notation of the ACE model, let me just go back quickly, that is to say that we usually find that the variance of E is larger than the variance of this thing, okay? Than the variance of C. Let me make one more point just about this figure while we were there. It is striking, and I remarked on this yesterday, it's striking that for years of school in cognitive skills and socio-emotional skills, you get correlations of about 0.2 among siblings who are genetically unrelated but reared in the same home. And that is a little bit higher than what we see in other, than what you see. So these correlations like an estimate of C square, right? And if that's not clear, I'm happy to explain. And the estimate of C squared that you get from these adoptees, from looking at adoptees, at least in these Swedish data, do tend to be a little bit higher than the estimate you would get from, say, comparing mono and dizygotic twins. So, and I think that's in line with what people have found in the US literature, and I don't think it's completely understood. One explanation that's been proposed, and that doesn't apply here, is that most adoption studies are like inherently limited by the fact that you usually end up serving the children when they're still in the home or in the late teens. And to the extent that you think that the heritability is changing over time, that may just be that you're gathering your data at an age where the heritability is lower, and the C-square estimates are high, parameter values are higher than with twins. But that's not an explanation here because all the data are measured at age 18. Okay. So those are the three laws of behavioral genetics. And then Turkheim goes on to say, make a bunch of remarks I think are very much in the spirit of what I've been trying to convey, namely the heritability in and of itself doesn't invalidate environmental explanations, but it certainly suggests, and it might mean something very different for a trait like height, or as opposed to a trait like, say, your attitudes toward abortion or something really complicated. And that's because we think, we think that there are good reasons to expect the genetic effect on one of those outcomes to be a lot more proximal for them, to operate through a lot more proximal mechanisms than the genetic effects on the other one. But once you realize that that's how most people interpret these numbers, I think if anything, that the appropriate criticism becomes, okay, so what do I do with it? Why is it relevant? Not, oh my God, if this is true, it's the most important discovery since Newton or something. Okay. Okay, so I'll end with this slide, which is from a recent paper. That was an amazing empirical undertaking. They went out and they gathered, Polderman et al., they gathered data, it was in Nature Genetics, they gathered data on every published twin study. In fact, chances are that there are people in this room whose data are included in these graphs. And I think it's hard to, I think the results are kind of just a visual, allow you to sort of visualize some of the Turkheimer's findings. Here we're showing MZ twins, MZ twin correlations for a bunch of different traits, DZ twin correlations. The MZ twin correlations are consistently higher, and typically by roughly a factor of 2. And the fact that they're roughly twice the size of the DZ correlations means that if you apply Hawkins Formula on average, you get a C-square of 0. I don't think that's necessarily the case. You should conclude from that observation that C-square is 0 because we don't know that Hawkins Formula is based on the correct model. But anyway, be that as it may. Oh, I made a remark earlier also about how in practice it's almost never interesting to look at female and male twin correlations separately. That is, the female MZ correlation and male MZ correlation are almost always near identical for virtually every case I've looked at. And this graph is just showing that this is the aggregate, and the two next bars are like the male and female correlations. Maybe there are traits for which there are exceptions, but I don't see any of them in these figures. Okay, and finally, I think this is just showing like heritability across traits. I suspect that if you dug into this and estimates of C-square separately by males and females again, it looks to me that you're getting remarkably similar estimates. And this is Turkheimer's first law in action. These numbers are consistently higher than these numbers. And I guess to like infer Turkheimer's third law, you'd have to sum this number with this number to figure out what E squared is. And if you did that calculation, you'd see that E squared is going to be something in between, right? So because the three have to sum to 1. So that this is a figure version of Turkheimer's three laws. Okay.
So if you had all the adoptee data too, then you've got a separate thing for the C-squared, and then you can get the non-additive component. So is there a generalization of the size of, so you have monozygotic, dizygotic twins and adoptees?
Yeah.
Then
Absolutely, yeah.
and so what is the, suppose you did a graph of that, of the non-additive component across traits.
Yep.
What would it look like?
We can do it now. So we'll pick a trait. I guess you have to pick one of these three traits. So let's see, what would we conclude? Yeah, so the adopted correlation gives us C-square. So we can just substitute that in to the moment conditions to make life easy, and then we could back out what we would get. So let's do that. Well, let's maybe pick a trait where there is some non-trivial amount of C. Let's do error years, just because it's the SSGAC after all. Okay, so from the so what do we have that H2G. So let's call that like broad sense heritability plus 0.21. This is, of course, we're still making the assumption that the covariance of these U square terms are the same in all time. Okay, we have rho dz equal to some parameter of resemblance that I called alpha, H2G plus 0.21. Those are our new moment conditions, and now somebody can tell me what alpha is. That's one way to do it, right? And that would tell, so the alpha parameter would tell, an alpha of a half would tell us, okay, it's all the data are consistent with all gene action being additive. A parameter of over a half would actually tell us something interesting about, that would potentially indicate that there's a lot of assortative mating, or there's some other model misspecification, because with random mating, this parameter is bounded at 0.5. And if you get a number below 0.5, then that means that there's a substantial amount of gene action. You could also, an alternative parameterization that might be more illustrative is to say this. I'm going to take the additive component and call that H2A. I'm going to add a term that captures all non-additive variants, so any epistasis, any non-additive gene action. I'm going to add 0.21. I'm going to do the same thing for DZ twins, but I'm going to fix this parameter at a half, so sort of maintaining the assumption of random mating, and then I'm going to estimate some resemblance for this non-additive component among DZ twins. And if that parameter is, say, that parameter would tell you something about the mix of dominance and epistasis across the extent to which those two things contribute to overall phenotypic variance.
When you outlined the three assumptions of the ACE model, was random mating one of them?
Maybe not, but it probably should have been. Yeah. It's a good point.
What's the gene action you mentioned for the less than a half?
Yeah. So with random mating, with random mating and narrow heritability explaining all the heritable variation, so no non-additive genetic variance, then this number is equal to half, and that's I think you show that on the problem set, right? So we work that out on the problem set. but you do need to make this. You do make an assumption when you solve that. When you show that of random mating, and without random mating, it's no longer true that it's equal to a half. So that's actually something that was incorporated into in the model used in the social attitudes paper in '86, but not subsequently. Yeah, and that is actually and failure and if the only model violation is that you don't have non-random mating, but everything else we assumed is true, then actually your estimates are going to be of heritability going to be downward biased. Yeah.
Is there a reason why we're imposing the assumption that the non-additive effects affect the monozygotic and diazotic differently? In other words, the two equations like alpha is in the second one, but alpha is not.
Yeah. So are you asking why this doesn't have a coefficient in front of it? Yeah. And the reason is that monozygotic twins, they are genetically identical, right? So if there's an interaction between locus 1 and locus 13, that interaction is going to be the same for the two of them, barring some very strange thing happening.
When you're saying that non-random mating would downwardly bias it, you're assuming like positive assortative mating?
Yeah, I'm assuming positive assortative mating, and I think that that's always what happens. Yeah.
Can you walk through using the height correlations? Can you walk through how well the additive model fits the data?
Yeah. Okay. Sure. I mean, there are many ways to do that, but let's start with Falconer's formula. So what estimates of heritability would Falconer's formula give us? It says double the difference in twin correlation. So the moment condition is, under the ACE model, A squared is equal to twice rho mz minus rho dz. Okay, so we plug in so our estimate is just going to be to plug in these two numbers. Somebody will have to do the algebra for me, point for 4182, is that right? So that's a twin estimate. What other estimator do you want to use? Shall we do full SIBs?
Sure.
Go ahead. By the way, I guess we should also give a c squared just for. So what do we get for c squared? So that c squared is going to be 11, right? Because a hat squared plus c hat squared is going to be equal to the monozygotic correlation of 0.93. So let's just do, as an example, let's do the full SIBs, full SIB comparison. The full SIB comparison gives us, so there we actually have two moments. So we could actually estimate it from, let's do it both ways. We could just estimate it from full SIBs reared apart. So there the assumption, what's the moment condition? Well, the moment condition is just that in fact, that was on the slide earlier, right? The moment condition is that rho full SIBs apart, if they were randomly assigned and all that good stuff, is 1/2 a squared. So our estimator is just going to be, maybe I should call this twins or something. Estimator F is going to be twice times rho hat FSA, and that's going to be equal to 0.92. And you can do it other ways. You could take the full SIB apart, full SIBs together correlation. You could subtract our estimate of c square and double that, in fact, and that would give us an identical estimate to what the twin estimate, and that's obvious because these correlations are the same. So, right? So you could have done the ACE model, but comparing monozygotic twins to full SIBs together, and as long as you're willing to make the equal environment assumption, you get the same number. Adding
Monozygotic, dizygotic, and adopted.
Yep.
It looks like there's evidence of positive assortative mating.
Yes. Yeah. And of course we know that's true, and that's something that's been known for a very long time, and which of course suggests that the model. And this is exactly the process by which you iterate on these estimates and fix issues. So if we just start with the twin correlations, we end up with a conclusion that c squared is 0.11. We then look at the adoption data and the other estimates. They, if anything, seem to suggest a higher estimate of heritability, a lower estimate of c squared. Okay, maybe our model is misspecified. Let's add assortative mating, and off we go. Yeah.
You also, in response to Lauren's much earlier question,
yes.
said that you could. She asked about how well
Yeah.
the
So let's think back to James's question about, to James's movie yesterday with showing the identical twins, right, who shared all kinds of quirks. So it depends on like the order of the interaction, but DZ twins have a much lower probability of sharing the specific. If this is explained by like interactions between genes at different loci, then the probability of DZ and full siblings reared together happening to share the same gene combination that gives rise to the interaction is a lot lower, but it's still higher than for any random pairing of individuals from the population, and it's lower still if you once you go to once you look at half siblings. So the resemblance of this factor H2A decays from 1 to 1/2 for full siblings, to 1/4 for half sibs, to 0 for adopted siblings. The decay of the non-additive components, well, it depends on the degree of the interaction and whether we're talking about epistasis or dominance. But dominance decays at a faster rate, so that's separately identifiable, and epistasis faster still. And to say just how much faster, you have to specify the exact model of epistasis or epistasis that you have in mind. I think that the theory on this was derived by a guy called Oscar Kempthorne, and I think that's what actually, in one of the slides, I think that's what Dan used. It was his slide. That's what he used here. So here we're showing the first 3 terms from, like, I guess, a model where we're sort of allowing all kinds of higher order interactions. Like the next term would presumably be h squared dd, and then we could in principle have higher order interactions, in which case the decay is even faster, right? Because then you have to share a particular genotype at 3 loci in order for the interaction to kick in. We don't think that's a very important source of variation in practice.
So one direct measure of assortative mating would be the correlation with step parents. If you had, I mean, of course you could look at the correlation between the parents themselves, but I guess if you had step parent data, but
So usually what's done is, so these days you can estimate with molecular data, but yeah, usually what's done is you just estimate, try to back it out from the spousal correlation. I'm not sure, so explain what you mean by step parent, correlation between step parent and who?
Step parent would have a correlation with the kid only because of assortative mating.
Oh, okay. That's actually interesting, yeah. It may be that, I haven't seen that idea in use, but maybe.
That would be assortative mating plus the nurture effect.
Yeah, so maybe there are ways that step parents could give you additional identification. I've honestly never thought about it. Yeah.
So if I'm understanding it correctly, given the results, you can, given the downward bias, you can imply that it might be because of the positive assortative mating, but there is no way you can incorporate it in the model and get identification. Is that correct?
Oh no, you can incorporate it. If you only have twins, you can't. But if you have a lot of independently informative moments that you can get sample estimates for, then you can incorporate it. In fact, this.
Is it ACE model?
No. So if you're estimating an ACE model and all you have is twins, you are there's not much you can do. I mean, you can go multivariate, so it's complicated. If you do something like a multivariate analysis that looks at 2 outcomes and you're willing to impose some additional restrictions, then you can actually say something about assortative mating. That was done in a paper by Bierman, Taubman, Wales in the late 70s. Basically what they did is they estimated this parameter with just twins, but it's because they had data on, I think, earnings, education, and maybe something else, and then they imposed some additional restrictions. I forget what it was, but it's sort of but with multiple outcomes, it makes sense that you'd be able to do that. But I'm not sure if I'm understanding the question. Yeah.
Well, I guess my question is, so if you wanna see how important positive associative
Yeah.
mating is, you would have to make additional assumptions.
Yeah,
Because
yeah.
there's no way to
Yeah.
get it.
Yeah, from just the twin correlations is not, that's not where I would look for evidence on sort of mating. I mean, they can contribute along with other data, but just twin data alone doesn't seem like a good place to start and finish. Okay, speaking of finishing.
Yes, so, thanks.
Okay, thank you.